So today we are very fortunate to have with us Dapo Afolabi. He comes to us from University of California, Berkeley, where he's been working with Professor Shankar Shastri, and I believe just recently defended his PhD. So much congratulations. So Dapo works in the areas of autonomy, artificial intelligence, and perception. So these are all, of course, topics that are very near and dear to our heart here in the GRASP Lab. So we're really excited to have him come and talk with us, and he's going to be describing some of his recent work on scene understanding. So with that, take it away.
Hey, thank you, CJ, for the introduction, and it's an honor to be here to present my work in front of you guys, and I'm really excited to do so. So I will just go ahead and share my screen. Please let me know if that doesn't work out. We tested this earlier, so it should be fine. Great, can you see my screen? Just a thumbs up or?
Yep.
Okay,
yep.
Great. So I will just go ahead and start the presentation. So great, thank you guys for being here. Today I will be talking about data-driven perception for autonomy. And basically, I think maybe where we can start off is just going from an intuitive understanding of perception and some of its applications. So, perception is everywhere around us. So starting from, most applications we use, so think about autonomous driving applications, there's perception involved. You think about personalized robotics or domestic robots or just general robotics, perception is involved. Or even in humans, right? So for example, take the scenario here. At a party, you have to be able to differentiate between the voice of your friend talking to you and all the other voices in the crowd. Perception is also involved. And intuitively, we understand what's going on, but a useful framework to think about perception is to maybe think of perception as a system that takes in some input data about an autonomous agent and its environment, and tries to transform this into useful information that can be used for planning and actuation and effecting changes in the environment that the autonomous agent is interested in. So for example, here you have a perception system that takes raw data. So here it's just, for example, an image, which eventually is just binary data that you're converting to say, hey, maybe there's a table in this image. And to give another example, just to get us grounded, we can think about an audio signal system. So you take in audio signals and you want to convert that to meaningful information for some tasks. So maybe you want to take a sound and turn it into yes. So maybe that lets you know the people you're interacting with want you to do something. And another example could be taking IMU data and converting it to robot trajectory over time. So this, again, you're taking raw data about an autonomous agent in the environment and converting it to useful, meaningful information for a task at hand. Okay, great. And the title is Data-Driven Perception for Autonomy, and the main idea is why data-driven? Well, perception systems have been worked on for many, many years, and we've achieved a lot of progress. But there are certain cases where it makes sense to take a data-driven approach. And my presentation today will focus on some of these cases. And I'll highlight 3 of these cases here. So one of the cases includes when we're trying to model human behavior. So if you have a perception system that involves modeling human behavior, then it might make sense to take a data-driven approach, because it might be difficult sometimes to try to extract exactly the correlations that you're looking for when you need to model human behavior in perception systems. Another example would be when you try to make tractable approximations for functions that you're using in a perception system. So for example, if your functions that you're using, you're trying to optimize over them to estimate, the state of the environment or the state of your robot. And, these functions are not tractable and involve a lot of compute to be able to get anywhere. They may be using data-driven systems to make tractable approximations is the way to go. So thanks to the growth of deep learning, we can use some of these data-driven systems to make great function approximators that we can use in optimization and things like that. In other cases, we actually know what the system is. It might just be very difficult to model or very complex. And it might involve a lot of human interaction. So we need humans to sit down to think about the system, model it. And if we try to scale up these systems, it becomes very difficult because you always get that human input. A data-driven approach can also help in this case to reach the skills that you want. Now, just my philosophy in general is not data-driven everything. I understand and I advocate for balancing between data-driven approaches as well as modeling physical systems. And I think they're very complementary in the sense that we should take advantage of both whenever we can. Okay, so what I will do, because this is a perception talk, and perception is applicable to many things like I just showed in the introductory slide, what I will do is I will focus on two of these reasons because of time, and I will give application scenarios where we've tried to model human behaviors or try to give tractable approximations or model complex systems. And I'll talk about perception systems in these examples. And so that's basically going to be the roadmap. So today I will talk about two cases. So one will be in autonomous driving and the other will be in 3D shape and pose estimation, which is more geared towards the mixed reality application. So let's see these applications. So first we'll talk about modeling human behavior, as this is one of the use cases for data-driven approaches to perception. And in this, the application for this scenario is autonomous driving. So basically I've titled this part of the talk as people as sensors, and hopefully it becomes clear why this is the case. So the scenario we're going to focus on would be an intersection scenario. So for example, you have to intersect with pedestrians at a crosswalk or other vehicles at a crosswalk. And specifically, we're going to focus on a scenario where potentially the sensors of the autonomous system are occluded or just fail. And this is a motivating example where on the left you have a top view and on the right you have a front view. So what's going on here is you have a crosswalk and you have a pedestrian potentially there. So we can see from top view that the potential may cross the crosswalk, but from the front view, let's say the red car is the autonomous vehicle and the black car is just another vehicle on the road. We can see that visually we can spot the pedestrian because it's occluded by the black car. And this could be a very dangerous scenario because if we don't know there's a pedestrian there, we might just go ahead and end up hitting the pedestrian. And so what we want to do is we want to say, what can we do to make this more safe? What can we do to detect the pedestrian in the case where we have sensor failure or occlusion? And just so that you know this isn't a made-up scenario, this happens quite a bit actually, especially with humans. So I have at least 10 minutes of videos from YouTube showing humans behaving in this way, where they make very, very dangerous moves because they can't see what's going on, they're just not paying attention. I will spare you the 10 minutes, but I will show you 1 minute of it just so you get the importance of the problem. So let's see, hopefully this works. And what you should pay attention to is we're always seeing things from the point of view of the person closest to the crosswalk. However, just pay attention to the other drivers on the road and see how they behave because they can't see what's going on. Okay, great. So maybe, hopefully that conveys some of the point that the problem isn't just made up. And it's quite important to take care of, especially if you want autonomous vehicles on the road. If you paid attention, you'd have noticed that usually the other vehicles are doing something. They're slowing down when they're close to the crosswalk, but there's just always one vehicle that just refuses to slow down, isn't paying attention, isn't seeing what's going on. Well, that kind of gives us an idea for like maybe what we can do. If we notice, right, so the question is, how can we improve safety or for down pedestrian detection in these scenarios? And if we paid attention, you kind of see that the humans can perceive the danger based on the behaviors of others. And this is kind of the intuition that we want to capture. So we want to ask ourselves, we know that the actions of humans can help provide useful information when sensors are occluded. How can we incorporate this action to provide safety? And so that's what we're going to do. So specifically, the way we're going to model this problem is to say that we're going to treat it as a mapping problem and use that as a proxy for detection. And mapping in mobile robotics refers to the problem of being able to estimate the state of the environment of an autonomous agent. And concretely, we're going to break this problem down even simpler and make use of an occupancy grid mapping approach. So in an occupancy grid mapping approach, the environment is split up into a grid, and every grid is represented, the environment is represented as a grid of n cells. So each grid will contain a binary random variable, where the random variable just tells us the probability of that grid cell being occupied. And basically, we collect all these random variables to represent the environment in another collection of random variables M. And before we go on, we're going to define some other random variables and then try to define the problem we're going to solve. So for example, we're going to define a sequence of random variables z1 to t as representing sensor information from time 1 to t, where big T, or the time 1 to t is the time of interest, and x1 to t representing the autonomous agent pose from time 1 to t. So for example, the autonomous vehicle. And A1 to T representing the actions of other agents from time 1 to time T. Okay, and finally, like I said before, we have this collection of states representing, of random variables representing the environment that we're interested in. Okay, and so we know from previous work from any robotics textbook you look into, you will find an occupancy grid mapping approach. Basically, the way we can think of trying to estimate the environment is trying to find this distribution here, or estimate the most likely state of the environment under this distribution here. So that's what we will initially want to do. However, we want to incorporate the actions of the other agents on the highway and see if we can do a better job than when we don't. And so what we want is to be able to estimate this distribution. So we want to estimate, how likely is this map configuration of the environment given the robot pose, the sensor data, and the actions of other drivers on the highway. Okay, so the way we can do this is very simple. We can make use of Bayes' rule here. And basically that's just what this equation here is saying. And what we need, because we know how to do, get this prior term here. So we can get the map based on using occupancy grid approaches, the denominator we can get from marginalizing. And what's missing here is this, this part highlighted in red. And this is what we'll call the driver model. So we need to model the behavior of other vehicles on the highway based on the current configuration of the environment, the state of the autonomous agent, and potentially all the sensor data we're getting. Okay, and that's what we're going to try to do. And here's where the data-driven part comes in. So here we have to model human behavior. And what we want to do is ask, how can we do this? So the way we approached this was to first say, okay, we need a data-driven approach. We need data to start off with. So to do this, we sampled people and we asked them to interact in a simulation with other pedestrians at an intersection scenario. And so doing this, we conducted a bunch of experiments and we're able to record over 1,000 scenarios of human drivers interacting with pedestrians. And so what we recorded in every scenario was the velocity of the human driver, the acceleration, the distance to the crosswalk, and the occupancy at every given point in time. And now we want to take advantage of this and learn a driver model. So I put an image here that I will come back to, but it's just a primer for what's going on. So first we define these variables that we've collected: velocity, acceleration, and distance crosswalk, and we cluster them in space. So we cluster them and we define these clusters as our set of actions. So intuitively you can think of them as, when we look at these clusters, we might see something like moving fast toward the crosswalk, moving slow, accelerating, decelerating, stop, things like that. And then given this, we also have the occupancy that we recorded. And we split our data up, and learn this empirical distribution. So basically what you're looking at is, if we look at the region, for example, in this image right in front of the driver, so you have a region here, and for example, this could be an occupancy grid. We're saying, given this occupancy grid, what's the probability of seeing some of these actions? So in this case, let's say the pedestrian is off on the right or something, we're more likely to say, okay, it's moving fast because the pedestrian is on the right of the road, and so there's no one in front of it, it can move fast. Okay. So we make the assumption that, given the map of the environment, the autonomous vehicles pose, as well as the sensor data obtained by the autonomous agent, is not important for predicting the behavior of other vehicles on the highway. And the reason why this makes sense is because, one, the relative location of the agents we're looking at. So usually the autonomous agents is behind the other drivers. Usually we're looking forward when we drive, right? So if we have a map of the environment, we're not looking backward and trying to say, okay, what is the autonomous agent doing? And we use that to make a decision. But one can also potentially incorporate some of this information going forward. And so this is what we do. Again, going back to the equation, once we learn this driver model, we can plug it back into the equation, and we have the regular occupancy grid mapping that gives us a probability of M given X and Z. And basically what we want to do is see, does this approach work? Yeah, so this is just going back and iterating through the steps we use in producing the results we want. So now what we do to test this is to say, we have data which we split, nicely trained validation test, and we want to say, now we're going to introduce an autonomous agent. So initially what happened is we had human drivers interacting with pedestrian. Now we're going to add another lane and add an autonomous agent. And what we want to see is, as the autonomous agent, which will be the one in red here, is moving, eventually it'll get occluded by the human vehicle and the pedestrian could be moving. We want to see how well does it estimate the state of the environment compared to, like, let's say not using this information at all. And so that's what we do. We use this equation here to get our new estimates. And the next slide will show you some of the initial results. Okay, so basically, let me break down what's going on here so that it makes sense. It can be a lot to just one slide. But the way you look about this is, think about the top half as one result and the second half is another qualitative result. And so basically what's happening here is, to the left is our work and to the right is just a standard approach that doesn't make use of this information that other vehicles on the highway are providing. And basically what we can see in this occupancy grid is darker regions indicate the grid cell has a higher probability of occupancy, and lighter regions indicate that the grid cell has a lower probability of occupancy. And so what we see here, for example, is that we can predict, even though our sensor is occluded, that there's most likely no pedestrian in front of the driver and that there's a pedestrian on the other side. And also here we can predict that there's most likely a pedestrian in front of the driver and nothing to the side. And just looking at it doesn't make sense. But intuitively, what we see is that, if I told you, like, what we see from data is that in this scenario, the blue vehicle, which is just another vehicle on the highway, is moving fast. And so now it makes sense, right? Given the video we saw, if the vehicle is moving fast, unless the vehicle was crazy, which is an assumption we're making, that the human drivers are not crazy. So unless this driver was crazy, you wouldn't be going really fast if there was someone in front of you. And if you're slowing down in front of a crosswalk or stopping in front of a crosswalk, it doesn't make any sense to just stop, because unless there's someone crossing, because there's no stop sign there. And so we're able to capture this intuition from data and able to model behavior of the human driver and incorporate it in a useful way that can provide safety through pedestrian detection. Okay, and also for some quantitative results, we measured the similarity between the ground truth map that we collected and our predictions. And here we use an image similarity metric. And what you need to know is lower is better. So what you see is over time, the results we get. So this on the left side is the average, T0 is the initial starting time, T equal big T is the end time. And we can see that we provide some significant improvement over, saying, oh, my sensors are occluded, I don't know what's going on. And here, so the point here is, being able to use the data-driven model for perception in this autonomous driving scenario and show that it's useful. So this is just one example, and hopefully this, starts to convince you that, hey, this is actually a useful approach for trying to solve some of these problems. And the next one I'll talk about is trying to make a tractable approximation for functions that you might be using in your perception model. And concretely, like I mentioned before, you might have functions that you have to optimize over that just very complicated or not tractable. And so they will involve lots of compute unless you make some nice approximations, which is what we're going to do. And a use case here is in shape retrieval and transformation estimation. And some of the applications, because some of this might be vague. So the problem here is, we see a shape, we want to know what is this shape and what is its relative pose and scale compared to maybe something I've seen before. And so some of the applications here are in mixed reality. So for example, you take this virtual tour of a house, which kind of is going up due to, unfortunately, COVID. But what you want to say is, you could tour the house, and if you could understand what's going on in the scene, right, you could say, okay, I don't want that coffee table anymore, or I don't like the position. I want to, manipulate it. I want to rotate it or replace it with something else. So if you can understand what's going on there, you can make some of these changes. And the way we say understand is, you see the shape there and you say, okay, this is what it is. This is the pose and scale relative to what I know. And therefore I can make these changes. And, and also in scan to CAD applications for mixed reality, you scan an indoor environment or an outdoor environment, and you want to make it nicer, easier to edit, easier for people to understand. You want to fix some of the problems with missing data, occlusion, things like that. And so you want to convert it to a CAD model. And one of the ways you can do this is to try to understand what's going on in the scene, to match the objects, know their shape, their pose, their scale, and compare it to maybe a CAD model and try to find the nearest neighbor or closest representative model and use that in your CAD representation. Of course, this is not limited to mixed reality. Also, you see some of this is useful for robotic manipulation as well. And so I'll just go into the problem and say, what we want is we want to see a shape and we want to say, okay, what is this shape and how is it related to things I've seen before in the past? And maybe an inspiration for doing this is a process of introspection, which isn't 100% reliable all the time, but is a good guide for trying to maybe start with some algorithms that are tractable and you can use to solve the problem. So we can imagine a human in their thought process. So they see, for example, a chair, and they're thinking, what is this thing? And so they go into their memory and say, oh, I've seen so many chairs before. Now I'm going to do some sort of template matching to figure out what it is, as well as figure out what is its relative pose and scale relative to what I've seen before in the past. And so concretely, we can write down a problem as saying, someone gives us an input database of shapes, right? And we say that these shapes are all in some canonical pose and scales. So for example, all of them are unit normalized to a unit sphere, and they're all facing the same direction. So all the front directions face toward the y-axis, for example. And this is reasonable because a lot of the large-scale data set, take ShapeNet for example, it's easier to collect data in this way, where everything is normalized and easy to work with. And now someone's going to give us a query shape that doesn't necessarily have anything, well, not have anything, but isn't necessarily in our data set. And what we want to do is we want to estimate this query shape. We want to find it in its canonical form relative to our data set, as well as the similarity transformation. So there's a scale, rotation, and translation to convert it from this canonical form to the query shape we're interested in. And some of the assumptions we'll make, for example, is that just to make life a little bit easier, which we can relax some of these assumptions, is that the canonical objects all have the same class. So for example, they're all chairs we're talking about, all tables, or all beds or something like that. Okay. And so this is an overview of the approach we're going to take, and I will go into detail. So this is just like a bird's eye view of what's going on. I will go into detail of each section. But what's going to happen is, someone gives us the input data. We're going to convert it to something that's useful for us. We're going to learn a representation that's helpful for us. And the main point here is, like I mentioned before, you can do some template matching with your data set and try to find the right shape if that's what you want. So by scanning through data set. But the problem that comes in here is that one, if the shape is not in your data set, then you run into some problems. what would be useful is somehow, given the data that we have, if we could expand this set of shapes so that we're more likely to find what we're looking for. And so this module here will help us in doing that, as well as provide an approximation to a function that's otherwise, not tractable. So if we had to do the template matching, we might have to like search through all the possible shapes that we have in our data set, and that could easily take a lot of time. But what we can do is if we can learn a function that maps from the shape space to maybe some other vector space or d-dimensional space, then maybe we can do a search in this d-dimensional space that helps us find what we're looking for. And we do the optimization, which you can think of as this search in d-dimensional space to get the right parameters. And then we convert it back using standard Martin-Cube techniques to, for example, a mesh that we can work with. And finally, we note that this process that I'm going to present also provides a compact representation for the environment. So that by itself is another benefit that helps us in, let's say, compressing representation, which is useful for mixed reality applications where you have to share data continually. Okay, so basically, before I go into details, I'll need to go over a couple things just so that it makes sense to everyone and you're able to follow along. So you might already know this, but just for the sake of everyone, I will go over this. So first is a definition of an SDF or sign distance function. So this is just an implicit representation of a 3D shape, or it can be used to represent a 3D shape. What's going on here is a sign distance function is a function where at each point in space, we return the signed distance of that point to the surface of an object. So given a shape, at any point in space, we say, what is the distance of this point in space to the surface of my object? And the sign tells you whether or not the point is inside or outside your 3D shape. Okay, and so for example, this is an implicit function, and we're used to a lot of implicit functions. So for example, take the equation of a circle, x squared plus y squared minus r squared is equal to 0. So here this is a circle radius r, and what's going on is the 0 level set of this function gives us the surface of the circle, so the set of points that lie on the circle. And a sign distance function is very similar. So given some 3D shape S, we're going to define the set of points inside and on the shape as omega s, and the boundary set of points as d omega s. And then we just say x is some point in 3D space. So technically and concretely, phi here is our sign distance function. So phi at a point x for a shape, omega s is defined as this. And basically what this is telling you is for any point x, the sign distance function returns, the distance to the distance of the point to the surface of the shape, as well as the sign telling you whether or not it's inside or outside. So that's the intuition. The equation might look a little bit ugly, but that's basically what it's saying. And it has been used for lots of 3D representation, as you can see here. And this is kind of the representation we're going to use going forward. Okay. The other thing we need to know is what happens when we have to the sign distance function of shapes that are related by similarity transformation. So given a similarity transformation, so a scale, rotation, and a translation, and two shapes, S and S prime, that are related by the similarity transformation, so that one is just a transform of the other, then we know this relationship to be true. So the sign distance function at any point in space for the transformed shape is just a scaled version of the original sign distance function of the original shape at this the pre-image of the point under the transform. And basically what this is telling us is that we have a way to relate two shapes. If we have a way to relate two shapes using a similarity transformation, that we can also relate their sign distance function. And finally, remember the equation, we'll come back to it, but finally, we also need to present some data-driven approaches for representing shapes, which we'll take advantage of. So first thing I'll talk about is implicit functions and deep generative models for representing shapes. So what I've shown here is some of the approaches in literature. But what's going on here is I just mentioned the sign distance function as a function, and we know neural networks or deep neural networks are function approximators. And people in literature have come up with ways of marrying both things. And so we have ways that we can represent shapes using neural networks, and some of the results. But what's really interesting here with these generative models is that they kind of learn this latent space where if we search over this latent space, we start seeing new shapes that are plausible for the class of objects we're looking at, but maybe we're not seen in the training data set. Now, the advantage this gives us is if we use this representation, then we could expand the set of data, the data set that the user has given us to query over and get many more shapes. So we're more likely to find what we're looking for. And basically the way this works is, you have a set of shapes, and for each shape you assign some code. So the code is going to be a vector in some D-dimensional space, so living RD. And what you want to do at first is to say you want to learn a model where for each shape you want to say at any point X, let this model approximate the signed distance function for that shape represented by the code at the point X. And intuitively, you can think now if we vary the code, we start seeing new shapes. And that's the point here. So again, this is a data-driven model for representing a function that otherwise would be difficult to do. And what happens is, one benefit, it's an approximation that's useful for us. And also it gives us this extra representation power because it produces this new latent space that helps us find new shapes. Okay, so now that I've presented some of the preliminary work, I will talk about how this falls into the presentation here. So concretely, again, we're given this set of input shapes. And what we want to do first is learn this, generative model over the set of shapes. And like I mentioned before, this gives us two things. One, it gives us a way to search over this input set of shapes by providing a mapping between the set of shapes and a vector space. And also, it gives us more shapes than were initially provided because this latent space here has many more shapes than we initially have. And the next thing we do is we convert the query shape into a signed distance function. So one of the assumptions implicitly that we're making is that our shapes have a signed distance function representation, which is relatively a mild assumption because for any shape representation, you can easily convert to a signed distance function. So now we have a function that gives us the mapping that we can search over, as well as the signed distance function representation for any shape. So that's the data we need. And now what we're going to do is that we're going to try to solve this problem, which I will motivate in a second, but we're going to do this search over this space to try to find both the right shape, but as well, we want to find the right transformation parameters. So we want to find the right scale, rotation, translation, etc. And then go ahead and get the shape that we're interested in. And so I've just put it on the slide here. And this equation here might be kind of, you might be curious where did this come from. But remember the representation, the equation I asked you to keep in mind, where if two things are related by some scale, you have this relationship between a signed distance function. And essentially, we're going to make use of that. So what I've done here is I've just written G inverse explicitly. And I just put the scale in front of phi, which is now approximated by f hat. So that's our deep generative model. And basically what we're trying to do is solve this optimization problem here. So, this is good, but the problem is we also like for, anyone to be able to use this, we like to make this easily implementable. The problem is, if we try to solve this, say, for example, using gradient descent, we run into problems doing gradient descent over a space of rotation matrices. And while it can be done, we'll like an easier approach. So what we can do is just re-parameterize the rotation so that we can put it into, some open source package that everyone uses. So for example, let's say PyTorch or TensorFlow. And that's basically what we're going to do. And to re-parameterize it, we're going to make use of the axis angle representation of rotations, where omega represents the axis of rotation and theta the angle of rotation. So omega here, we're going to restrict to lie on the unit sphere. And omega hat is just a conversion between this representation to a skew symmetric matrix, as is written here. And the additional thing we're going to do is we're going to use spherical coordinates to rewrite this omega, because it lies on the surface of unit sphere, we can do so. So if we restrict R to be 1, this will be fine. And so we can re-parameterize the rotation as being a function of psi and rho and theta, where psi tells you the elevation or inclination or angle, and rho tells you the azimuthal angle. Okay, so now given this parameterization, we can just plug that back into our equation. and we have this this equation here, where now we can plug this into some open source automatic differentiation engine and use it for solving our problem. So now it's easier to solve compared to, and it takes less time than doing this template matching over and over and over again. Okay, so this is the approach we're going to use, and the question is, does this work? So we're using a gradient descent approach to try to solve this optimization problem. One of the problems with gradient descent is that you might get stuck, or it's prone to get stuck in locally optimal points. So one of the questions that might be interesting is that, if we start relatively close to the optimal solution, how often do we end up at the optimal solution? So that's what we're going to try to quantify next. And so the first approximation we're going to make, or the first assumption we're going to make here, is that let's make the problem a little bit simpler. Let's say we know the axis of rotation, right? So there are only 2 of the parameters that are out of the way now. We only have fewer parameters to solve for. And this is a reasonable assumption because a lot of shapes usually lie on a flat surface. So they're lying upright on a flat surface. So if we identify this flat surface, then we can use the normal to the plane representing this flat surface as the axis of rotation. So this is it's not difficult to obtain. And so we're going to define some extra variables. So we're going to say if S is the true scale and delta S is some region around the true scale that we can draw the initialization from, then we can say S0, which is our initial initialization for the optimization scale parameter, is defined as this. So intuitively what this is saying is, let's say I know or my S up to my scale up to delta S%, so let's say 30%, and I initialize anywhere within 30% of the true scale, how often do I get to the right part, the true scale? And we do the same thing for the other parameters here, translation, and that's just the initialization parameters. And to make the problem a little bit fair, we randomly initialize the true scale, so uniformly from 1/2 to 2 of the initial shape we're looking at. And the same we do for rotation. All the variables can go from -π to π. And the translation, we randomly initialize it within a radius of 4, so everything is in meters. So the shape could be from 0 to 4, or -4 to 4 here. And we test this over 4 different classes of objects. So for example, chair, table, desk, just to make sure it generalizes a little bit. And also we tested for each class, we sampled 30 different shapes from ShapeNet dataset. And for each shape, we conduct 50 trials where we randomly initialize this optimization problem, where you have the initial shape that has been scaled, rotated, translated randomly, you don't know, and you want to approximate it. And so to make this more concrete, we initialize our change variables, or delta variable, that's saying we know the scale, let's say up to 30%. The translation is off by, let's say 15 centimeters. And we know the angle of rotation up to 20 degrees, right? So we know the axis of rotation. So these are the variables we're interested in, as well as the shape. And so we solve the problem and we try to quantify it. So what we use to quantify it is something called the F-score. And what you need to know is F-score is a metric that goes between 0 and 1, with 1 being the best, meaning 2 3D shapes are exactly the same if the F-score is 1, and 0 meaning the worst. They're definitely not the same. And so what I will show you is some of the results we obtained. And what's important to note is we want to quantify in each trial, how likely are we to get to the right result. So this is what we see. And basically I've plotted this using box plots, where the orange line shows you the median score for each range. So the box plots, the way we read it is, between what are the range F-score between 0.9 and 1, 0.8 and 0.9 is represented by this box plot, 0.9 and 1 is represented by this box plot, and so on. And what this tells us intuitively is, if you do this 50 times for each shape, most of the time, so 40, let's say 45, 46 times, we get an F-score that's between 0.9 and 1, which is good. So this tells us intuitively we can expect that this will work given the range of parameters that we initialize it over. And then these ranges are not difficult to obtain. One could use some other estimation algorithm to try to get here, or if you wanted, you could use brute force to kind of grid up the space and then use this as a final way to approximate the result. And another way to kind of measure how well we're doing is to measure the error in the angle of rotation. So that's what we do next. And what we see here, again, is that most of the time, our error is less than 1 degree. So this is very good. It means that, you know, we're able to not only, in both metrics, it's telling us that this is very likely to work. And so next we say, okay, what if we don't know the axis of rotation? So let's take that out. And so that's what we do here. So we allow the phi, the rho variable and the psi variable to vary within 10 degrees. So we don't know each parameter up to 10 degrees. And we do the same thing and we solve the optimization problem and report the F-score here. And as we can see, it doesn't, the performance doesn't degrade significantly. You almost can't tell unless you look at it carefully. So again, this is telling you, yes, this can still work given the initialization ranges that we present here. And so this is good. So in theory, this could work. That's what it's telling us. So now we want to try it in practice. So we need shapes that have been scanned in the real world, and we want to try to see if we can figure out what it is based on data set we have, as well as the transformation that gets us there. To do this, we make use of publicly available data set. So this is Redwood Dataset, which contains scans of 3D objects in the world. And what we do is, again, we assume that we know the axis of rotation, because as you can see, a lot of these objects are lying on the floor and upright. And so we can tell, you know, we can fit a plane to the floor and find the normal. We have the axis of rotation. And so that's what we're going to do. We're going to use the shapes as input shapes, and we're going to use our algorithm, given the data set being, let's say, some CAD data set, for example, ShapeNet. And we're going to try to see if we can estimate what the shape is, as well as the transformation parameters. Okay, so here are some of the results. So what you're looking at on the left is the input shape from the Redwood dataset, and all the way on the right is our result. And what you should be looking at is the gray shape is the prediction, and the red shape is the ground truth. So I've overlaid them on top of each other so you get some intuition for how accurate it is. And here we compare to do 3 different approaches, where what you do is this sort of template matching, where you have to search through the data set first to find the right shape. And then once you find the right shape, you try to estimate the transformation. And as you can see, we're doing better. So what we've done is we've used classical handcrafted features for some of these shape as template matching. And then we've also used a deep neural network for template matching. And the point here, what this is telling us is, you know, if you do this 2-step approach where you do template matching and then some transformation estimation, it's very likely that, you know, you mess up on the template matching, and then your transformation estimation cannot correct for that. And so you have this compounding problem where you get this, the error just propagates itself. In addition, because there's, we also enjoy the benefit that the set of shapes has been drastically expanded. So now we're more likely to find shapes that maybe were not in the data set initially. And this is some of the things, some of the results you see indicating this to be the case. And so here are more results showing you how well our shape, we understand the shape as well as the transformation parameters related to it. Okay. And so here are some quantitative results that kind of back up the idea. So again, the F-score, we can see ours is doing significantly better. And again, this is because of this compounding problem and this limitation in the initial data sets that you have. So both when we kind of do this joint estimation with a larger, more expressive data set that we learn from this latent, get from this latent space, we're able to do significantly better. And here we see the benefits of using a more data, driven approach. And where we have this function approximation that helps us, do better than we would otherwise if we did not take advantage of it. And the other thing I mentioned is, our latent space is this d-dimensional representation. So intuitively, we can think, oh, we have a d-dimensional vector, as well as some scale parameter, rotation parameters, which, you can represent with a few parameters. So if we understand the shape and the right transformation parameters, we actually have a way to compress the shape. So what we'll do is see if we can actually take advantage of that. And this is useful for applications, again, in mixed reality, where you have to transform data, transmit data quickly and multiple times. And what we do is we're going to compare it to classical approaches of doing compression on, let's say, meshes. And so we'd use vertex clustering and quadratic edge collapse. And what I show you here, let me interpret it for you, is if you look on top, so you have the F-score, which kind of tells you the representation power of each of these approaches. And each of these approaches have parameters. So for example, for the quadratic edge collapse, you can reduce the number of faces, desired number of faces, or you can increase it by a factor. And what's going to happen is, as you do so, you kind of lose out in representation power, but you save in memory that you're using to represent the shape. And the same thing for vertex clustering. What this tells us is that our algorithm provides a sweet spot between representation power and compression power. So if you look at it, we're providing very similar representation power to some of the best results here. However, what's important to note is that we're doing so at 20 times less representation power than some of these other approaches, right? So we also, not only can we understand shape, but like as a byproduct, we're also able to compress the shape very well. Okay, so now I'm going to talk about, I've just presented this here, and I'm now going to talk about the power of using this data-driven approach, this optimization framework, and how you can incorporate other things as well. So as an extension, we can look into a lot of man-made scenarios where you have reflective symmetry. So humans love symmetric things. It's really easy to do, it's visually appealing, and it's everywhere around us. And now we have a data-driven approach that can help us take advantage of this information. So what we're going to do is we're going to say, if we can detect this symmetry, so for example, we represent this reflective symmetry as some function h, then we can enforce it in our problem as using this equation here. And intuitively, what this equation is saying is that the sign distance function representation under a reflective symmetry should be invariant. And so that's why you have this extra penalty term. And so what I'll show you next are some results for this work, showing what can happen when you're able to include reflective symmetry and things like that in your estimation approach. And so what you're looking at here is some input shape. So this is an occluded shape. So usually, when you scan, you might just see half of the object, or it might be occluded by something else. And now we're given this input shape, and we want to say, can you tell me what the shape is, as well as the transformation parameter relative to what you've seen before. And so this is a result without symmetry. So some of the approaches are showing promising results, but you can see some of the lack of data is hurting in some cases. Now, when we include symmetry, with here I've shown the planes of reflection, we can see that we not only get more complete shapes, but we get more visually appealing shapes. And so this is something that's relatively easy to take advantage of because of the way we've presented the problem. So not only can we do better than some other classical approaches, but now we can incorporate some other useful cues in the environment that give us robustness to things like occlusion or missing data. And the other thing we might want to take advantage of is if we look at, for example, an indoor scene, we might notice that a lot of times shapes are repeated. So you can just look around you probably find a chair that's repeated in your environment. So people buy things in pairs. Dining table, you have a bunch of chairs, they're all the same. Now, this is useful because if you have a shape that's occluded and you have multiple of them, each of those shapes will be occluded in different parts. So if you can think about it intuitively, you put them together, they're all the same shape, you get a bigger picture. It's like, multiple repetitions tell you a different story about the same shape. And basically, we can do this again and plug into our optimization problem, where all we're doing is we have multiple optimization problems where they're all constrained in the latent variable, so the shape has to be the same. And so I will show you some of the initial results that we have. So what you should look at is the top is one result, the bottom is another result for a different, and we kind of split them up. So we have 4 different results here. So this is 1, 2, 3, 4. Okay. And so this is what's happening is you have repeated objects. So for example, you have 3 chairs, the same chair, it's just in different pose, different scale, different level of occlusion. And we can solve this problem like we proposed before, where we do the solution for each of them individually. So here without the symmetry constraints involved. But what we can see is that, if we treat all of them as the same shape, use that information, now we can get even better results because we can see that, each of them tells us a different story about the same shape. And so that's what's going on here. So each of this is just 3 repetitions of the same shape. And when we incorporate all the information together, we get much better results for understanding and shape modeling. And yeah, so these are some of the results. We can see even with very severe occlusion, we're able to produce meaningful estimates. Okay. And so going forward, I'd just like to know, what can we do with this? What other applications can we do? We can understand the scene. What can we do? So one of, like I mentioned, this scan to CAD application, what we've done is we've represented objects, but one school of thought is that, any indoor scene can be factored into a layout plus an object. And so we've said, okay, we can see the objects and we know their transformation. And what we need now is just, let's see if we can model the layout. So we just test this out using the approach that we described, and we collect some data for layouts and we try to model them. And indeed, we can model it. And what's really interesting is we have a variety of shapes that we can model. We don't need to make any assumption about, the orthogonality of walls or like some Manhattan assumption. We can model very complex shapes, both planar and non-planar. And so this gives us a way where we can, now say, can we use all that we know and apply it to a real world problem where we can model like an indoor scene. So here is a scan, for example, and what we've done, we've taken the scan, we've taken the data. So this is a real scan actually, and it has just been like touched up to clean it up, and the visualization has been done really well. And what we do is we take that data, we transform it, and we have a new representation for it. So now we can see in our model of the scene, we know what the shapes are, we know the relative transformation, and also we can compress that data, right? And so we do this again for other scenes so that you can see. And some of this, we haven't done any symmetry inclusion here or repeated objects, and this is some of the work we want to include in the future. But we can already see that we have some pleasing results already. So what does this do? This gives us, these are all the benefits of what we can do when we can use a data-driven approach to provide a tractable approximation to some function that might be otherwise very, complex to model. And we can use this in a perception algorithm. We can understand what's going on in the scene, and then we can use that to model as well as do many other applications. And so maybe let's just think about it in the road ahead. What can we do with like some of these approaches? I mean, so one of the things I mentioned, but I never really talked about in detail, is this robotic manipulation. So we've shown that, okay, we can use the space of shapes. What if we could get a space of instructions instead, So when we know like a shape, we know, for example, a chair in the image, we know how to manipulate it. What if we see a new chair, right? Maybe we can say, okay, now we can generalize and say, we don't need to try to figure out how to manipulate this new chair again. We can generalize the instruction from the old chair to the new chair, which kind of intuitive, right? Humans don't like learn how to manipulate every chair every time. Like, there are a few principles you keep in mind, and then you generalize those going forward. And also, we've talked about this 3D scene representation, where if you notice, a lot of things I've talked about are how to model the scenes using higher level representation. So here we're not treating every point in the scene as just by itself, or we're treating it as an object, which is part of a larger picture. And so we can take advantage of things like symmetry, repeated objects, which we can't if we just said everything was just a point in space. And we use classical 3D reconstruction approaches for representing the scene, for modeling the scene. So the question is, what other higher level information can we take advantage of? So for example, one here is a wireframe representation. And other things are, how can we merge this with lower level representation where we treat each point as just a point and we try to do some classical 3D reconstruction on that so that we can obtain some finer details on top of this representation that we've presented. So that's what's being shown here. So it's buildings with very fine details. And also, how far can we take this? I've shown you just a room. Can we take this to city scale? Can we try to use this outdoors where we can actually get applications for mixed reality that are actually very impactful for everyday life? And finally, also, I've mentioned perception that you can use for pedestrian detection. And the question is, now that we know the pedestrian is there, what can we do? How can we design control strategies to make sure that the autonomous vehicle is actually behaving in a safe way? And finally, there's so many applications for perception, data-driven perception, ranging from robotics to energy systems to mixed reality. And the question is, how can we take advantage of this? So for walking, for tactile feedback, for energy systems, the list just goes on. And we need to start thinking, we have this powerful tool that has blown up in the past couple of years. How can we take full advantage of it for solving some of the most difficult problems that we're facing today? So yeah, that's most of the presentation. Thank you guys for listening to me, and think I should be here to, if anyone has questions to ask, but yeah, hopefully this has been useful for you guys as well. Thank you.
That's a great job.
Thank you so much, Dal. That's a really, really wonderful talk. As per usual, we're happy to entertain questions from the audience. Gabby, I'm wondering if people have the ability to speak up now, or should we do it by the chat?
They can ask questions via the Q&A. Oh, sorry, Gabby, didn't realize you're back.
Yeah, they can ask questions through Q&A, or if they raise their hand, I guess we could allow them.
Okay. All right. Okay. So I guess there was one question that I had. I wanted to sort of. Okay. Yeah, I guess actually Kostas just beat me to it. Kostas has a question about 3D reconstructions. That your results really look very, very interesting, state of the art. Can you explain sort of how you actually pull out these axes of symmetry? Where do you, how are you able to, is this part of the optimization procedure, or do you discretize over it? I'd be curious to sort of, get your intuition on how that gets done.
Okay, great question. So actually, I think Kostas' question is kind of related, but may not be exactly the same. I'm not sure if it's both of them, but I'll try to do my best to answer both. So starting with your question, how do you get the access of the symmetry and going for it? So in the work we've done, in the presentation I've shown, we've just manually gone there and tried to label it and identify it. But actually, we're working on follow-up work. That's it's quite relatively easy to do this. We've just done this just to show, but one approach is just like for example, there's a lot of work in literature. You take a ransack-based approach for detecting symmetry. There's a lot of work on partial and approximate symmetry detection, which we want to incorporate. But the point here I was trying to present is, if we know these things, right, we can take advantage of them in ways that could be really helpful. So right now, in what I presented, this was manually done for identifying the symmetries, but we're working on ways to incorporate this, and there's a lot of work in literature that we can already do some of these things. And to answer Kostas' question, the two parts. So one, we didn't have to know the axis of rotation. So I presented some of the results I presented was, what if we didn't know the axis of rotation exactly? But what I was saying is, it's relatively cheap to actually figure out what the axis of rotation is, because a lot of shapes are just, a lot of objects are just lying on a flat surface. For example, you saw the chairs or the tables, and so it's relatively easy to do. So if we have that information and we know we can do better, why not do it? Of course, there will be cases where we don't have that information, but algorithm still provides a way to give you solutions in those cases, and that's what I showed with the second graph. I'm not sure if you remember. I can pull it up again, but hopefully that answers your question.
Okay. All right, I'm going to take advantage of my position here and just ask another one. You made this sort of very tantalizing comment about sort of using symmetry as a way of actually getting around Manhattan assumptions and other kinds of limitations like this. I was curious to just hear you expand a little bit on that and how that how you sort of see that working.
That's correct, but I think maybe the main point I was trying to push there was symmetry and repeated objects. So these are cues in an environment, and what we can use it for, one is we can use it to get robustness to occlusion and missing data. So occlusion and missing data, you get that a lot when you do this scanning of the environment, because objects are not just nicely put out there. And the problem is, what do? How do I make up the rest of the data? So there's work using generative models to kind of do this, but another more natural approach, I believe, would be taking advantage of some of these cues in the environment, which you can't always do. Not every object is symmetric, but if you can, you should use it and try to get some more robustness. And also in addition to robustness, it gives you this visually appealing result, because a lot of man-made structures are just naturally symmetric. So that's what I was trying to push there. And some of the stuff for the Manhattan assumption, a lot of that is just due to the way you can generalize, that you initially can't do, if you didn't use this generative models. You can generalize to new shapes, new curves, things like that, that you don't have to make the Manhattan assumption. On the flip side though is if we can make some of those assumptions, how can we incorporate it into some of the work we're doing? So we might be, if the assumption is true, then we might be able to get even better results. And I feel like the optimization framework we've presented gives us the ability to be able to do that. And that's what I was trying to hint towards when I said, what can we do to take advantage of some of this more higher level information, like wireframe representation, Manhattan assumptions, things like that. So the thing here is, if we know something, we should use it. Or if we don't know it, maybe this data-driven approaches can also help us when we don't have, we can just say, okay, this assumption is true, even when it's not true.
Okay, fantastic. All right, great.
So I've got a question, just kind of follow up.
Yes.
So on do you have examples of, when you make an assumption, for example, in Symmetry, where it hurts you? Like you see a data that looks like something and you assume the symmetry when in actuality it's not there?
So let me see if I don't have a picture here, but let me see if I understand your question. So you're saying, is there a case where, let's say we assume symmetry and it's not actually symmetric, and then that becomes a problem?
Right.
That's what you're asking, right?
Yep.
Okay. Yeah. So I mean, I haven't tried that because I guess maybe it's a bias from my own looking. I was trying to show something else, but good question. But naturally, yes, that's a problem. It's what we do is we add a penalty term to the optimization problem, and naturally, the penalty term is saying this thing should be symmetric. So we're more likely to produce symmetric looking objects. And if it wasn't symmetric, then we run into a problem because we're introducing a bias here that isn't actually there. And it's, in the worst case, you can think of it as, you have a constrained optimization problem where you've just nicely moved yourself away from the true optimal solution by saying it should lie in a set where the solution actually doesn't exist, or the solution is not in the set. So yes, you might, it might not be severe. Also, the nice thing here is that you can tune the penalty term by decreasing it so that, it's not so effective. And in doing so, you might be able to say, I'm not so confident about this symmetry thing. Maybe I shouldn't penalize it a lot for doing so. But yes, it can hurt you, but you can produce very symmetric looking shapes when in fact, it's not actually symmetric. Unfortunately, I don't have a picture here. I'm showing you some of those examples.
Thank you.
Right. So again, for the audience, again, if you want to speak up, I think Gabby can unmute you. Otherwise, there's the Q&A on the right. Yeah, I know that we're all getting used to this brave new world, but okay. All right. Let me ask them just sort of one more question. Is in the first section, you presented this work and sort of posed it in the context of this of an occupancy graph. But the interesting thing about the objects you're talking about is that they sort of have intrinsic dynamics to them, and that they're where traditionally occupancy graphs have been sort of phrased as more static.
Yeah.
But clearly in your case, they actually evolve. I was just wondering whether you, how you sort of think about that, or.
So that's actually a great question, and it's something we actually want to follow up on, because what would be great is if you had a way to, one, it's hard because it's humans we're dealing with, right? So humans are somewhat unpredictable. So again, maybe this is a case where you can use a data-driven approach to kind of model the dynamics of the human and somehow propagate that in the environment as well. I mean, there's other approaches to doing so, making assumptions like, let's say, constant velocity, things like that. But that's something you can incorporate as well. It's a great question. The standard occupancy grid is made for static environment. And what we've just shown here is that, the main focus was trying to say, can we somehow show how to incorporate the intuition that we can learn from other people's behaviors. And if we incorporate, these dynamics of the environment as well, then everything I presented still holds. All you have to do is just change, your method for producing the occupancy grid. Actually, you should get better results in those cases as well. So it is helpful. It's just not something we've we've tried to tackle in this problem, but definitely it should be looked at.
Okay. Well, all right.
A follow-up question, again, exploiting the advantage of being a panelist. So in the example that you showed, one of the videos, a lot of these accidents happen because of limited information, because someone ahead of you sees part of the road that you don't.
Yes.
And you would never try to be aggressive in situations. An autonomous car would not want to be aggressive in situations where it does not have information like this. So what is the goal here? Is the goal to predict a better world around you, a better locations for all the objects around you? Or is the objective to kind of be a little more aggressive when you drive? Because, for instance, you can imagine that a car would be safe if it did not try to do any of these antics.
Yeah, so I mean that's a good question. The thing though is, like, if you look at some of this, it could be unsafe to do something that's not natural. So for example, in this intersection scenarios, there's actually no stop sign, right? So if you're just, like, one of the things they tell you in driving school is, yes, you don't want to be going over the speed limit, but at the same time, you don't want to be going too slow because you're putting other people's lives in danger, right? They're not expecting you to behave in that way. So I guess what this does is it gives us, yes, you're correct, we can be a little bit more conservative in our behavior and try to promote safety in that case. But one of the benefits of this is we start looking at ways to say, well, maybe we don't have to be so conservative. Now, I'm not saying this like solves the whole problem. I'm just saying we can start thinking about that. Let's take advantage of all the information we have wherever it is. And maybe we don't have to be so conservative, like, right? So maybe I don't have to be, driving super slowly. I could get to my destination a little bit faster. At the same time, I can be safe, or I can be more safe than I would normally, like if I didn't take advantage of all this information. But care has to be taken, right? Again, it's the same thing with the assumptions we're making. We have to be careful in how we incorporate these things into our systems. We don't want to be making assumptions. For example, the assumption here is that a human driver is not crazy, or they haven't seen something, right? So what if the human driver in front of you is just really, likes taking risks, and so they just go right ahead, even though there's a pedestrian. I mean, that has happened to me a couple of times, right? If I'm just going off their behavior solely, then I will just go right ahead too, and then I'll hit the pedestrian, right? So we have to be careful, but at the same time, we don't want to be too conservative. So it's like, where can I find that sweet spot? Where can I take the most advantage of information I have? And how can I incorporate that safely as well?
Okay, yeah, thanks.
Okay, thank you.
Okay. Well, all right. Great. I guess I'm not seeing any more questions, and I guess we're a little bit over time. So I guess I really want to thank our speaker. So yeah, it's a really great talk. I very much enjoyed it.
Thank you.
And yeah, we have the rest of your schedule for today lined up. So I believe you're meeting with Dean Kumar right after this.
Yes, that's correct.
Fantastic. Well, again, thank you very much, and look forward to chatting with you more a little later today.
Thanks. Same here.
Take care.
Okay.
I think Vijay is muted.
Dapo, we have to switch Zoom sessions, I believe, to get to our meeting.
I will do that. I think Gabby sent me the link, so I'll just leave this Zoom session and I'll join.
Or I can text it to you if you want.
Oh, okay, that's fine. Thank you.
I don't know if Zoom will allow you to Zoom automatically from one Zoom session into another, but we'll give it a shot.